Good morning. Today I'm going to show you how to take a layout drawn in an AutoCAD or other mechanical tool and to rasterize it for an inkjet printer. So we're starting with the DXF file, and we don't rasterize DXF directly because there are a lot of problems with DXF. There's so many ways to draw things that the results and what the user intended are never quite the same. So our preference is to convert it to Gerber, where we can check the correctness of the output prior to running the RIP. So I'm going to show you what we have here. It's basically some test patterns. We have some nicely curved lines here. They're about 100 microns in width there. We have some straight lines. We have some straight lines with bends. More straight lines with bends. Here we have some concentric circles which form rings, and that's going to require us to use the de-embedding feature in the conversion, because otherwise the outer ring would cover everything. And here we have some little rectangles. Now these are drawn with lines, as you can see, and they form some kind of a rotary encoder or something similar to that. On the outside we have a polyline of 0.1 millimeter that acts as our boundary. And then there are various squares here drawn with closed polylines, and some little tiny what appear to be circles, and some other squares and circles here. Okay, so that's our test vehicle, and this is all drawn in millimeters. The overall distance is about 200 millimeters here, and as I said, our feature sizes are in the order of about 100 microns, 75 microns. All right, so now we're going to run the conversion. All right, to convert from AutoCAD to Gerber, or from DXF to Gerber, I should say, we're using the ASM 500 program, and it takes you step by step through the process. So we'll start by selecting the DXF file, and I want to use the one called Test Vehicle Cleaned, because that's the one I edited. I need to make sure I enter the units of millimeters. So I click OK, and it scans the file. Now I'm going to configure the translator. I have several things to configure. First, I can set my Gerber settings. I'll have my Gerber in millimeters, format 4:4. In my translator settings, I'm going to make sure that I have link lines and arcs on, so that those little lines get linked to closed boundary. I'm also going to turn on my de-embedding without cut lines, and I'm going to make sure I have 274x output. So those are the things I need to set. The other thing I've done is I've set my arc resolution on my arcs down to 2 degrees so that I get some nice smooth arcs, so that I don't see any jaggies later on in my output. Now I'm going to define an aperture table. And here's the apertures I'm using in Gerber. These are essentially little drawing tools. I have a basic round one of 0.01 millimeter, 10 microns. Now these POEX are special ones. They're used as the definition of an outline of a boundary, and everything inside is filled. They don't have any width, so they're set to 0 there, but those are the ones that will define most of our work. And finally, I have another round one which matches the exact width of my outline, and I'll make sure that my program uses that one to draw the outline. So that's basically it. Now I'm going to select my layers. The only layer that I care about is called Pattern, and I make sure that the Fill mode is set to Outline. And I also make sure that my Trace mode is set to mode 1, so that that path I have that's 0.1 millimeter will get transferred into a 0.1 millimeter draw in Gerber. My output file will be called pattern.gerber. Now that I've set everything up, I click Start Translation. And we don't have to worry about those warnings. It simply can't find some font files. And now we'll view our Gerber data. So there's our Gerber data. Let's center it. And let's zoom in and see what we have. Let's zoom in this area, and you can see that we have our same curves, and you can see that they're filled. So that'll be our arc test. Over here are our parallel lines. Over here are our bent lines. Now here's our concentric circles, and because I used the de-embedding option, you see that instead of this outer circle covering everything, each time it hit a new boundary edge, it changed polarity. So we ended up with the same image that we thought we were going to have by using concentric circles. And then here I have my little encoder, and you can see that we have the areas we want filled in. Everything is pretty much as it should be. Here's that outline that I created, the 0.1 millimeter outline. So now we have a Gerber file. We should be able to run our rasterizer and produce a bitmap. We've created our Gerber file, and now we want to rasterize it. So we use the program called Gerber Rip, and this is actually an engine-based program, which is normally used by other types of programs. That is, it's usually wrapped around some kind of application. So I'm going to use it in command line mode just to show you what's done. The first argument is the actual executable called Gerber to TIFF, because this includes the TIFF formatter. And then this is our input file, pattern to Gerber. This says automatically compute the Windows extents. This tells us it's in millimeters. This tells us it's 274x. This says we want to produce TIFF, and we want the file name to be pattern2540.tiff. This says use 128 megabytes of RAM for your raster buffer. Probably don't need that much. This sets the DPI at 2540. So those are essentially the minimum requirements for the command line. What I'm going to do here is just type pattern.bat, and you can see it returned in less than a half a second, maybe a quarter second. And if we do a dir, we'll see there's now a pattern2540.tiff. So let's have a look at that. To look at the data, I'm using Artwork's very large bitmap viewer. This is a viewer that handles TIFF and BIMP files that are very, very large. That's implied in the name. It lets you pan and zoom and measure things. So I'm going to zoom into some of these critical areas here. Let's zoom into here. That's our curved lines. Let's zoom in a little more. And if we zoom in enough, we can actually see the pixel size relative to the line width. These lines are about 80 to 100 microns, I'm thinking. Pixel at 2540, I think it's about 10 microns. You can see the stepping is of course, unavoidable. And you can see how this is smooth across the entire arc. Okay, let's go back home again. Let's look at this guy here. These were our concentric circles. You can see what they look like at 2540 DPI. Let's go back home again and let's look at our friends here. These were these little parts of the encoder, and again at 2540. The results you're going to get, of course, are going to depend on your DPI. You can't expect excellent results if you only have a few pixels to image the line. So I thought what we might do is run this same job at a higher DPI and see what things look like. To do that, all I have to do is create another command line, and this time I just changed the DPI to 5080 and the output file name to 5080. Just run it here. And it takes a little longer. It's generating 4 times as much pixels. You can see that the 5080 TIFF file is about 91 megabytes. And this is uncompressed, by the way. I didn't ask it to compress it. So let's see what that looks like. And there's our 5080. You see it still opens very, very quickly. And let's have a look now in this range area here. Things are looking a lot smoother because we have, you know, twice as many pixels to image the line with. So looking a lot nicer. And if we look in here, you see that these look a lot nicer also. And one more, let's look at our concentric circles. You can see these also look much smoother. So as far as a test vehicle, rasterizing this is not a big deal. We rasterize much bigger files at much higher DPIs with the same software. But what's important, of course, is the integrity of the data, how accurately it comes to matching the input data. And you can see it's quite good. Thank you.